Another look at this interface. We'll simply repeat the show command. Up now we've dropped 183 packets. 183. Up to 190. And right now we see that there are 4 packets currently in the 5-packet buffer. Since our traffic average is 64K and the clock rate is 64K, we may be able to keep the frame relay switch from buffering and dropping packets by implementing frame relay traffic shaping R1. First, we create a simple map class with a CIR of 64K. We then enable frame relay traffic shaping on interface S00 and apply the class to del C102. Now we'll go back to FRS, clear the counters, and observe the buffer on S1. Note that we have 1 packet in our buffer, but we haven't dropped any. Let's take a look at this a couple more times. We have 3 packets, but we still haven't dropped any. 1 packet, 1 packet, no packets, the buffer's been cleaned out, so the frame relay switch is no longer dropping packets. Let's go back to R1 now and see what's happening there. The command show frame relay PVC 102 will show us the shaping details. Note the CIR of 64,000. The committed burst is also shown equal to the CIR. However, the byte limit is 1,000 bytes, as you see here, and the interval is 125 milliseconds, or 1/8 of a second. The committed burst is actually 8,000 bits per second. It is shown as 64,000 because we did not set it explicitly. Instead, we relied on the router to scale the interval. You see the default min CIR is 32,000 bits per second. It is half the CIR by default. Note that it says shaping inactive. This means that there are currently no packets waiting in the buffer. The output queue line gives us the details of this buffer. Note that a total of 34 packets have been dropped. Let's see how this buffer behaves as the traffic rate varies over time. This will give us the output for show PVC 102 for just the output queue line. Notice there are still no packets in the buffer, but we've dropped a total of 39. So the traffic rate at the moment is below 64,000 bits per second. We'll just keep an eye on this by hitting the up arrow and observing the result. Still no packets in the buffer. Now you see there are 7 packets in the buffer. The full show frame PVC 102 command would show shaping active at this point. The buffer has increased to 15 packets, so we appear to be at a peak above 64,000. Traffic is still increasing. We now have 28 packets in the buffer. Now we're up to 39, and you can see we're starting to drop more packets. The buffer is now shown full, and since the last clearing of the counters, we've dropped a total of 59 packets. Is there anything we can do to avoid these drops? Well, let's increase the size of the whole queue to the maximum 1,024 packets. And we'll repeat our show command. Notice our queue is now 1,024 packets rather than the default 40. It would take a very long traffic burst to fill this queue. The problem with this solution, however, is that it takes a long time to empty such a deep queue. Packets will suffer very long delay and jitter times. This is the trade-off for fewer drops. In this presentation, we discussed and demonstrated how FRTS could be useful in a traffic rate mismatch situation. In a later presentation, we'll demonstrate some of the advantages of class-based frame relay traffic shaping. When we discuss voice over IP over frame relay, we'll see how FRTS and class-based techniques can be combined to improve voice quality over frame relay. Cisco IOS provides three sets of tools for frame relay traffic shaping: GTS, FRTS, and class-based. Traditional FRTS uses the command frame relay traffic shaping on the physical interface. It is covered in other presentations. This presentation focuses on class-based shaping over frame relay. Like traditional FRTS, class-based shaping allows us to regulate traffic flow. Shaping buffers traffic when it's at its peak and sends the buffer traffic when the rate is below peak, helping us to avoid egress blocking and ISP policing. Also, like traditional FRTS, class-based shaping can create software queues at the interface, subinterface, and PVC level. These queues can then be managed to provide quality of service parameters like bandwidth reservation and priority service. Compared to traditional FRTS, class-based shaping allows us much more control over what traffic gets shaped. We can define classes of traffic based on complex matching criteria and then shape these classes to various rates. We can then combine these shaping policies with marking, policing, and congestion avoidance techniques. Class-based shaping uses the Modular QoS CLI, or MQC. We refer to the MQC as the Swiss Army knife of QoS configuration methods, since it combines many quality of service tools into a common framework. The basic MQC configuration method is to define the traffic of interest in a class map, apply policies to these classes in a policy map, and then apply the policy map to an interface using the service policy input or output command. There are two class map options that are useful only over frame relay. We can match on frames that have the discard eligible bit set in the Q922 header. We can also match on traffic arriving or leaving on a particular PVC. For class-based shaping, our primary shaping tool will be the command shapeAverage. It is with this syntax that we specify the desired committed access rate, committed burst, and excess burst parameters. The shapePeak command shapes at all times to the excess information rate. Few users find this particular command helpful. Adaptive shaping is implemented using the shapeAdapt command. It permits the router to throttle back its sending rate in response to beckon and fecken congestion signals. Traditional FRTS offers additional throttling options. The size of the shaping queue in packets can be controlled by the shapeMaxBuffers command. It ranges from 1 to 4096 packets and defaults to 1000. The fact that class-based shaping policies can be applied at the interface, subinterface, and PVC level add to both the flexibility and the complexity of this method. The level of application affects the number of PVCs that will be affected by the policy. Policies cannot be applied directly to the PVCs. Instead, they must be applied in a map class frame relay, which is then applied to the DELC. In traditional FRTS, we can also apply service policies to the PVCs in a map class, but these policies would not include shaping commands, only queue management policies like bandwidth or priority. To demonstrate class-based shaping, we have set up the lab you see here. A traffic generator is sending two flows of traffic through R1 and across the frame relay links to R2. We will want to apply policies to three different classes of traffic: The first one we call from 6011. This is traffic with source UDP port 6011 and destination UDP port 6016. This traffic varies randomly between 13 kilobits per second and 38 kilobits per second. It averages about 24K. Our second class we call from 6012. It is also destined to UDP port 6016, but the source port is 6012 instead of 6011. This flow has a constant rate of about 40K. Finally, we have the class 26016. This class is defined as all traffic with destination UDP port 6016. It will include both of the previous flows. As such, this aggregate flow will vary between about 53K and about 78K. It should average about 64K. The clock rate on FRS port S1 has been set to just 64K. Our traffic streams sometimes exceed this bandwidth, so we will implement shaping in an effort to get all the traffic across. We will then implement a bandwidth reservation to make sure none of the traffic from port 6012 gets dropped. Here are the commands that created each of our classes on R1. Note that each match statement references the associated named access list. The access list specifies the source and destination ports for the two classes and just the destination port for the aggregate class, 26016. To verify these flows and their rates, we have created a simple policy called count and applied it inbound to F00. Let's take a look at the results. Here you see the packet counts for each class averaged over the last 30 seconds. Note that class 6011 has been coming in at a rate of 20,000 bits per second. That's our variable flow of traffic. Class from 6012 is coming in at a steady 40,000 bits per second. Here you see the rate has decreased to 18,000 for this class. However, the other class is still a steady 40,000 bits per second. Now we will implement a policy to shape these flows so they do not exceed the 64K access rate between FRS and R2. We will apply this policy at the level of the physical interface to demonstrate the issues. The MQC process starts with class maps, moves to policy maps, then goes to application using the service policy command. However, it is sometimes helpful to analyze the process in the reverse order. Our service policy is applied to interface S00 in the outbound direction. It references a policy called shape S00. Let's take a look at that policy. It references a class called 6016-102. We will look at it in a minute. The shape average command specifies a CIR of 64K, a committed burst value of 8,000 bits, and an excess burst value of 0. iOS will calculate a committed burst value for us, but we needed to specify it here so that we could get past it in the syntax and enter a 0 excess burst value. Remember that if you do not set the excess burst value, iOS will set it equal to the CIR. If we allow this in our lab, then our shaper could send 128K after a long period of time below CIR. However, our CIR is already equal to the far side access rate, and any excess would just be dropped. Now let's take a look at our class map. It matches on our existing class that specifies destination UDP port 6016. However, there is an additional criterion. Matching traffic must be also on DELC 102. Since our policy is applied at the interface level, it would apply to traffic on all DELCs without this match. Unlike shaping